till now in this course we had been looking at continuous systems which are stationary, which are fixed to the ground, but there exists a class of continuous systems with very unusual dynamic characteristics, which is due to its translation. So, we will consider today in this lecture the dynamics of translating continua, translating strings. So, where do we find a translating continua? So, a common example is in the travelling thread line. In looms. So, a travelling thread in a travelling thread line, you have a string which is translating, and it can have transverse vibrations. So, this is one example of translating continua. The second example comes from cable cars. So, in a cable car there is a rope that carries this the cable car or the gondola. So, the string or the rope is travelling and the gondola or the cable car is attached to the string. So, this forms a translating continua or translating string. The third example is observed in rolling mills. So, in a rolling mill material is being rolled and the material is constantly getting elongated, and it moves at very high speeds, and it can move between two rolls and or one roll, and then this the dynamics of this material which is being rolled, it may be a bar or a rail. So, that has to be studied with that motion, the axial motion of translation that is imparted to this imparted in this rolling mill. Now, when we so these are a variety of situations where we find translating continua, but we are going to look at a very simple situation. We are going to look at a travelling string. And when we so we are going to study the dynamics of a travelling string, and when we study this we will make all the assumptions of that we had made for the string model. So, we are going to study the dynamics of travelling strings with the assumptions that we had made for studying the dynamics of normal stationary strings. So, let us look at this picture. So, here I have shown a string that is in translation. So, this is the string. It is travelling at a constant speed v. It is passing through two eyelets, and the length of the string between these two eyelets is L. So, we are considering a one dimensional continuum string which is translating. So, let us look at the dynamics. So, we will derive the equation of motion of this translating string using the Lagrange's equation. So, let us write down therefore, the kinetic energy of the string. So, if you consider the transverse displacement of the string at any location x as w x comma t, then if I draw this little element at location x, so this element has a displacement w x comma t and it is moving at a speed v. Now, this angle, so suppose this angle is theta, then we know that tan of theta is del w del x is approximately equal to the sine of that angle. Now, I can write this kinetic energy as half rho times a times dx is the total mass of this little element, and it's now it has got velocity not only in the transverse direction, but also in the horizontal direction, and the transverse direction velocity is a combination of this del w del t, which is the local time derivative, and there is a convective part because of its velocity. So, that the transverse component because of this velocity is v. So, if I write down this is v sine of theta and this is v cosine of theta. So, therefore, plus v sine of theta, now sine of theta is del w del x, so this square plus v cosine theta whole square. Now, with the assumption that del w del x is small, v cosine theta can be approximated as this, and therefore, if I integrate this over the total length of the string, I have the total kinetic energy of the string. The potential energy is same as that of a normal string. Therefore, the Lagrangian is given by this expression. Now, when we take the variation of this, So, here I have of course, a time integral. So, this must vanish. Now, I integrate by parts this term with respect to time, this term with respect to the space, and again this term with respect to space. So, this implies this term has to be integrated with respect to space, and this term also with respect to space. Now, this term gets derivated with respect to time, and there appears a negative sign So, we have these terms. Now, here by our standard arguments at time t 1 and t 2 there cannot be any variation of the configuration. So, these boundary terms must vanish, time boundary terms. Now, here we have the spatial boundary terms. Now, once again we use the same argument and say that we can vary the domain independent of the boundaries, and therefore, they must individually vanish. So, if that is done, then we finally have the equation of motion So, here we have one v additionally. So, these two terms add up to give us this 2 v w x comma x t, and this term comes from here, and we have this additional term from the potential energy. So, this must be 0. Now, this can be simplified by dividing by rho a, and I will write it like where c square is now this is the equation of motion of the travelling string. Now, here let us identify a few terms. This term is because of the Coriolis acceleration. While this v square del w del square w del x square, this term is the result of the centripetal acceleration. So, if the velocity of translation goes to 0, so these two terms will vanish, and then you recover back the equation of motion of a normal string. Now, the boundary conditions are obtained from the boundary terms here that you. So, these are the boundary terms. Now, if you so these two can be combined, and for our case that we are going to consider, the boundary conditions are simply and that actually makes the boundary terms 0 in this case. So, these are our boundary conditions. So, we have derived the equation of motion and the boundary conditions for the string. Let us quickly look at the string once again. So, here I am drawing an element of that string. Let us quickly understand this equation of motion that we have just now derived from the Newtonian approach. So, in the Newtonian approach, what we need to do is we need to consider a frame with this element. So, this is the tangential direction to the string, and this is a normal. So, this frame rotates. So, this angle is theta. So, the angular velocity of this frame, let us say omega, can be written as approximately w x t. So, it is del square w del x del t. So, del w del x is nothing but this angle, and rate of change of angle gives us the angular velocity. So, when we derive the equation of motion from the Newtonian approach, we must consider this motion of this element in a rotating frame. So, we have this Coriolis acceleration, normally we write 2 omega cross V rel. So, omega is a vector which is perpendicular to the plane of this paper, and V rel, the relative velocity with respect to this frame, which is at a location x. So, this frame is only giving the orientation, but it is located at x, it is not moving with the string. So, relative velocity is nothing but v. So, if you calculate the Coriolis acceleration, then it is 2, and this is the term we find in the equation of motion. So, let me write down the equation of motion once again. So, this is the Coriolis acceleration term, and in addition to this we have the curvature of this element. So, this element is moving on a curved path, and the radius of curvature, so the radius of curvature can be written as approximately so the curvature, which is 1 over r, is the double space derivative of the field variable. This is well known, and the centripetal acceleration is given by v square over r, and that turns out to be so these two terms we find in our equation of motion. So, when we look at the Newtonian approach, we have to consider these two terms, because we now have this element moving in a rotating frame. So, these two terms will naturally come. Rest of the Newtonian approach is same as that we have followed for the string. Now, look at this equation. You see, in a fixed string, we have the equation like this. So, this double derivative with respect to space also appears, but now this appears with c square minus v square. Now, there is a possibility that v might just equal c. In that case, this term drops out, and remember, if this term drops out, this term was responsible for the stiffness of the string, as we have here. So, the double space derivative is responsible for the stiffness of the string. So, when the velocity in the event, the velocity equals c, which is the velocity speed of transverse waves in the string, then the string loses stiffness. So, this is an unusual behavior that we see in a translating string. The second thing is this term, the Coriolis acceleration term. This has a single time derivative. Now, when we discussed damping, normally we had in the damping terms a single time derivative. So, the question might arise that whether this term is conservative or not. So, to see that, we will follow the procedure we had followed previously while discussing damping in continuous systems. We multiplied the whole equation with the velocity and integrated it over the domain of the string, and this happens to be this can be simplified and written like this. So, I can integrate over this spatial coordinate So, we have this velocity square computed at L minus velocity square computed at 0. Now, since we have considered fixed boundary, this turns out to be 0. So, this tells us that for the fixed boundary case, the translating string is conservative, rest of it, as long as C is greater than V, the rest of it is a conservative system. So, only this term now is also conservative. So, this does not contribute to the energy at all. So, for fixed boundaries, this term is conservative. So, there is a possibility that if the boundaries are flexible, then this system might become non-conservative. Now, let us look at modal analysis of translating strings. So, our equation of motion the boundary conditions are as usual. We consider as we have done before a solution, we search for a solution with this structure as we do in modal analysis, and if you substitute this in this equation and rearrange, then this can be written as so, this therefore, is our eigenvalue problem. So, this is our eigenvalue problem for our system. Now, first thing that strikes us is there is an imaginary coefficient with and there is an imaginary coefficient and there is a single spatial derivative of w. Now, it can be easily checked that this problem is non self adjoint. Till now we have whatever systems we have considered, they were all self adjoint. This is the first example which is non self adjoint and which makes its dynamics very interesting. The second thing is these eigenfunctions, the eigenfunctions are complex. Which we can easily make out from here. Now, so the eigenfunctions are going to be complex. So, let us try to solve this eigenvalue problem. Now, for this kind of system eigenvalue problem, let us assume a solution with this structure. So, if you substitute in here, here I must point out that this omega is the circular natural frequency of the system. So, this quadratic in k can be easily solved, and what we obtain these two solutions of k. So, from this quadratic polynomial we obtain these two solutions. So, therefore, our general solution of the eigenfunction may be written as in this form. So, this is the general solution of the eigenfunction, and this must satisfy these two boundary conditions. So, if you substitute in this solution in the boundary conditions, then we can write these two equations in a compact form. And for non-trivial solutions of D and E, what we must have is the determinant of this matrix must vanish, and that gives us so this is our characteristic equation. So, this is our characteristic equation from which we are going to get these circular eigen frequencies, and if you solve this, then omega gets indexed So, these are the infinitely many circular natural frequencies of the string. So, here you can immediately see that if the velocity translational velocity is 0, then it reduces to the circular natural frequency of a normal string. Now, here we have this term c square minus v square, again there is a possibility that this v might be equal to c, and as you well understand that when a system loses stiffness, its natural frequency goes to 0. So, when v equals c, natural frequencies go to 0, but what is interesting is all natural frequencies go to 0 when v equals c. So, in this figure I so, here in this figure I have plotted the circular natural frequencies with V over C. So, these are all non dimensionalized. So, as you can see that for all the modes when V by C equals 1, which is V equal to C, all the natural frequencies, circular natural frequencies, they go to 0, and the variation you can see from this figure. This speed V equal to C is known as the critical speed. So, at the critical speed, the string, the translating string loses stiffness. Now, we have till now calculated the circular eigenfrequencies. Now, let us look at the eigenfunctions. So, these eigenfunctions therefore also get indexed, and if you substitute this omega n in here, and so when you substitute omega n here and solve for d and e, and you use those values of d and e in this eigenfunction expression. So, this is straightforward, and you can check that finally the eigenfunction are obtained corresponding to the infinitely many circular eigen frequencies. The eigenfunctions are obtained in this form. Now, you can immediately see that this is complex. Here d is an arbitrary constant which can be used to normalize the eigenfunctions. Now, so you see that these eigenfunctions are all complex. So, therefore, we can now write down our general solution using these eigenfunctions, and so linearly combining so we can write this as so this is our general solution, where B n and C n are arbitrary constants which will be fixed from the initial conditions. So, here immediately we observe that, so this first of all we have used this d n as So, the n can also in general be complex. So, this is the general expression. So, this is finally the general solution of our field variable. So, here you can see that space and time, they are no longer separated. So, here they get combined in these terms. Now, this immediately strikes us that this will make the orthogonality conditions a little difficult. So, we have a strictly non-separable solution. So, even the modal solution in particular mode, the solution is so, in general these solutions are non separable even for a modal solution. So, this structure of solution we will discuss further later in this course. Here the orthogonality, the way we have discussed it in this course till now, does not hold. It is replaced by something called bi-orthogonality. Now, we have been using this modal analysis or the modal solution for solving initial value problem, forced vibration problem, damped vibration problem, etc. And in every one of these problems we had to use this orthogonality to solve the system. Now, since this orthogonality is now non-trivial, so this becomes little cumbersome to use the modal approach for solving various problems for travelling strings, but there is a convenient approach which is using the Laplace transform technique. So, here I will briefly outline the Laplace transform technique for travelling strings. Now, in our force vibration analysis we had studied that the Green's function technique for solving this force vibration problems, and we have seen that if we can find out the Green's function of a system, then we can solve the force vibration problem for harmonic forcing, for arbitrary forcing, general forcing, as well as we can solve the initial value problem in a unified manner. So, therefore, let us look briefly at this Laplace transform technique for travelling strings. So, what we are going to do is we are going to essentially solve the Green's function for this system, because we as we have seen that once we know the Green's function of the system, then we can solve the force vibration problem with general forcing, we can solve initial value problem, etc. So, let us look at this problem. As we have discussed before, with this kind of forcing, what we solve is known as the Green's function. So, once we know this Green's function, then we can solve various problems for travelling strings. So, the way to do it is we will first take the Laplace transform of this equation. So, once you take the Laplace transform, you can easily check. So, suppose I define this as the Laplace transform of the field variable w, then if I take the Laplace transform of this equation and simplify, this is straightforward. So, essentially we are giving an impulsive input at x equal to x bar and at time t equal to t bar. So, once I take, so this is the final equation in the Laplace domain, where S is the Laplace variable. Now, you can solve this equation easily, but it can be further simplified if you use a transformation where alpha is, if you use this transformation in this equation, then this equation simplifies to with the boundary conditions, which are again obtained from here. So, you can very easily see that the boundary conditions here are for this in the transform domain, the boundary conditions are the same. So, this is the boundary value problem that now we have to solve, and with these boundary conditions. So, we have this boundary value problem, and with these boundary conditions we can attempt a solution So, because the boundary conditions are like this, we attempt a solution with this expansion using the modes of a normal string. So, if you substitute this expansion, so here of course if you substitute this expansion in the equation and finally solve for alpha s, alpha n, these are straightforward steps which can be done very easily. We have been following these steps before. So, if you substitute and then take inner product with these eigen functions, and finally, you solve for alpha n, here omega n are the natural frequencies of the travelling string. So, once you have this alpha n, you can substitute back here and you have u. So, if you have u, then you can substitute that expansion here to get w. So, finally, so this is the expression that you get. Now, here I have substituted the expression of alpha to finally obtain this, and if you take the inverse Laplace transform of this, which you can do very easily using residue theorem, if you do that, then this Green's function, so the solution is the Green's function, we can write this as so use residue theorem to invert the Laplace transform. Here it has got simple poles at plus minus I omega n. So, once you do the inverse Laplace transform, we can easily obtain this expression here. This is the Heaviside step, which appears because I mean from the causality condition that you are considering the Laplace this complex integral over a contour which closes the left half S plane when you do the inverse Laplace transform. So, you have to close on the left half S plane. So, this indicates that. So, from the causality condition. So, we have this Green's function, which is a solution of the travelling string with an impulsive force at x equal to x bar and t equal to t bar. This gives a solution at x t. And finally, for any arbitrary forcing q, so, if you have any arbitrary forcing q x comma t on the right hand side of the equation of the travelling string, then you can find out the response of the travelling string using this integral. So, let us see what we have discussed in this lecture. So, we have discussed the dynamics of travelling strings, we have performed the modal analysis of strings, and we have found that these eigen functions of the travelling string are complex, and the problem is non self adjoint. This makes the dynamics actually very interesting, though it is theoretically little cumbersome to handle, because now the orthogonality is replaced by bi-orthogonality, but then we have this Laplace transform technique and we have derived the Green's function for the travelling string. Now, once we have this, then we can solve the initial value problem, the forced vibration problem, etc., in a unified manner. So, so this gives us a very powerful way of approaching the dynamics of travelling strings. So, with that we conclude this lecture.